Okay, so what we're going to be doing now is we're going to be looking at part 3 of our circle theorems. This will be our final part. Now we're going to be talking about the lengths, meaning the distances from chords, secants, and tangents. So things that occur inside and outside the circle, how do the lengths of them related to each other, as well as the lengths of the pieces as they cross each other. Before we do that, though, we're going to review a bit of algebra. These are some things that are going to come up and be necessary as we go through it. So we're going to review some basics. We're going to start on page 9 of our notes. Again, these are all in sequence for circles. Should look just like that. All right, so the first thing we're going to do is we're going to learn how to multiply binomials, which means multiply two terms that each have two items within them. To do that, the first way we're going to do it is the way I usually do it in my algebra class, which is I use a generic rectangle, much like a Punnett square if you guys have done this in your biology class. What we do is we label the sides using each binomial. Okay, so the first binomial, x plus 1, stayed together, and x plus 4 stayed together as well. Now we look at each square individually. So first I look at only the square right here. Okay, and then I multiply the sides being x and x. That gives me x squared. And I do the same thing for each square, going to the top right. Now I'm going to multiply the 4 by the x on the left, the 1 down in the bottom left by the x, and 1 times 4 for your final square. Okay, from here we're going to write out everything we have inside and combine like terms. Again, this may be a new way of doing it, but combining like terms and multiplying binomials is something you've done before in Algebra 1. All right, we're going to look at a second way to do it, and that way is called FOIL. Okay, if you've never done FOIL before, FOIL stands for first, outside, inside, and last. So as you can see, we have FOIL, FOIL. So it just means you multiply all the pieces together. So I'm going to do the first two, x times x, which is x squared. The outside for the O, x times 4, which is 4x. 1 times x, which both of them are on the inside. And last. 1 is last along with 4. Okay, this method works just as well as the rectangle. We combine like terms, the 4x and the 1x, and we get 5x. The reason I don't like this one as much is because as you get into Algebra 2 and stuff, you have to multiply things that have more than two terms. And it's very easy to forget one and leave off a step. FOIL, the acronym FOIL, F-O-I-L, only works if there's 2 by 2s, basically, a binomial times a binomial. So if you extend that, FOIL doesn't really make sense anymore with the letters. It still works. It's just harder to make sure you multiply everything. Okay, the next thing we're going to do is a quick review on factoring. When I do factoring, I use a diamond problem and a rectangle. The rectangle serves very much the same way as the last one did, where we're trying to figure out a piece of the rectangle. However, in this case, we already know the inside of the rectangle. We don't know the outside. So if you remember a second ago, after we combined like terms, that's how we ended up with the x squared plus 8x type thing. So what we're doing is we know those two go there. Okay, just like before, those two are the x squared and the number, and what we did to get the 8 in the middle on the previous problem is we went ahead and we added the two things from those two boxes. So now the question is, how do I break up that 8? That would make sense in the problem. See, because I could do 1 and 8, 2 and 6. So just as an example, I could do 1x and 8x. And 7x. Those two add up to 8. However, there's no way to multiply some random number here that will give me a 7 and at the same time give me a 15 down at the bottom. There's no way to make that work. So you're going to have to find the numbers that work. Well, the way we do that is what we call a diamond problem. On a diamond problem, those two pieces at the end come together to make the top, and the middle term makes the bottom. And the goal here is we're looking for numbers to go in the blank spaces to the left and to the right that will add together to equal 8 and that will multiply to equal 15. So you can think about that for a second. Okay, well, if you think about it, what it is, it's going to be 3 and 5. 3 plus 5 is 8. 3 times 5 is 15. We have to include the x's on there because we have an x squared, and on the bottom we have an 8x. We're now going to bring those two into our rectangle, and we need to take a second to figure out what the outside is. The way I do that is I look at one piece at a time. So I've got my x. That would mean that has to be x. Then that has to be 5, and that has to be 3. So it kind of one piece goes at a time. You can also look and see this is the only way to make the whole entire puzzle work. And the last thing we do is we write our factors. Now remember, when we started, our binomial looked like a pair of parentheses. So that was when we were going one direction. We were multiplying to get this answer right here. Now we're going backwards. We're trying to go start from there and go to there. Well, our binomials, if you remember, we copied them to the outside of the rectangle. So our answer is the things on the outside of the rectangle. One last piece you may or may not remember from algebra is often what we do with these is we do set them up equal to 0. The reason is there are things called roots or solutions to this equation. So basically what it's saying is if this thing equals 0, what makes it 0? What are the values of x? Well, when it's just all mixed together like that, x squared plus 8x plus 15, it's hard to know. It's very hard to tell. When you factor it, a thing called the zero product property says that either one of these could be 0 and then the whole thing would be 0 because these are multiplied together. So what makes it 0 is -5 or -3 because -5 plus 5 is 0, -3 plus 3 is 0. And so therefore the whole thing would be 0. Okay, the last thing we're going to talk about is the quadratic formula. If you don't remember the quadratic formula, it looks just like this here. Negative b plus or minus the square root of b squared minus 4ac all over 2a. A lot of ways to remember it. I've heard songs. I've heard stories about boys going to parties. It doesn't really matter what way you remember it, just that you do remember it. The nice thing about the quadratic formula is that it gets you the answer to any x squared problem if there is a solution. Now, it can be no solution. It can be things that don't make sense. For what we're doing right now, we're going to get a solution because what we're going to be using it for is to find the length of something that we don't know, but we have to find it by using x squared. So we're definitely going to get answers to these. And when you look at this, there's this whole plus and minus piece. This is a question that gets asked a lot. Why plus and minus? Well, every time you have an x squared, just like last time we got -5 and -3 as answers, here we're going to get two possible answers anytime we do an x squared problem. However, since we're talking about real things in circles, we're probably only going to end up with one of our answers. If we get an answer something like 7 and -4, well, -4 doesn't make a lot of sense for the distance, a length of a side. So now what we're going to do is we're going to start substituting in. So as you can see, I'm replacing the b's with 5, c with -4, and a with 1. Now I'm going to go ahead and I'm going to simplify 5 times 5. I'm going to multiply 4 times 1 times -4 and 2 times 1. So that's the next step. Now I'm going to take those two minuses in front of the 16 and turn it into a plus. Combine 25 plus 16, which gives me 41. And now here we're done. So if you remember from before, sometimes that instead of a 41, it'll be something like a 36, and then you know, oh, square root of 36 is 6. If you don't know, like in this case, then you're going to have to leave it with the square root of 41 in there. So normally our answers would be the two things, -5 plus square root of 41 over 2, and -5 minus square root of 41 over 2. Like I've said numerous times already today, what's going to happen is a lot of times this right here will be disregarded by us because that right there is the negative answer. You're taking -5 and subtracting something away from it. That's only really going to work out in a negative number. And because of that, when you think about the length of a circle, it can't be negative. Okay, so the next thing we're going to do is now we're going to try to use this information to do some of the problems. You're not going to need it on every problem, but you might need it on some. So keep that note sheet handy. We're going to start now on notes 10, and we're going to start with a theorem talking about lengths of chords that cross inside the circle. Remember, the emphasis is do they cross inside or do they cross outside, because there's different rules. So when two chords cross inside a circle, so again, we're talking about them crossing inside the circle. There's no lines outside in this scenario. The product of the segments on each chord, okay, meaning when you cross, it's going to be broken into two pieces, is equal to the product of the segments on the other. So let's take a look at what this means. A lot of words for something very simple. So what this means is, as I break this apart, I've now broken this into two pieces. Okay, that's what that line does. It broke it into two segments. It's saying the product of those, okay, those two segments, is equal to the product of these two segments. So let's look at what that means. I'm going to put some numbers in there. You're going to have to write these on your notes. X and Y and A and B. Okay, what I'm going to do with those is, what this theorem says is, it says if you take A times B, it's the same as X times Y. So it's a very simple theorem. All it means is basically that when you multiply the two numbers on each side of the line, they equal each other. Okay, let's take a look at the first example. You're going to have to label the 3 and the X and the 4 and the 6. All right, so what this says is, it says that since 3 and X are opposite segments, they're going to be multiplied. And since 4 and 6 are opposite segments across the other line cutting it in half, therefore they're multiplied. And the ratios are equal. So 3 times X equals 4 times 6. It's a very simple problem from there. 4 times 6 is 24, and 3 times X is 3X. Now you're going to take 24 divided by 3, which is 8, and you've answered the problem. Okay, notice it does not mean these lengths are equal. 8 plus 3 is not the same as 4 plus 6. Close, but that's not the way the rule works. Okay? Because of the way the rule works, it's just saying the multiples are equal. It's kind of hard to believe sometimes. You know, for me, I sit there and I think, wait a second, what if my line is like way over here? There's no way that can be the same. Look how much longer that one is. Well, the reality is this might be a 1 now. And 1 times something is actually a pretty small number. So that may be 1 and 15, and this may be 5 and 3. It's not that unreasonable. It looks pretty reasonable to me. It seemed like it was way off, but the reality is they still multiply to equal 15. Okay, now if we want to make this problem a little trickier, we always talk about that, this is where you're going to do that. So now look, I've put X's on every single one of them. So hopefully you've copied that down by now. Okay, so what we're going to do is we're going to set it up just like normal. We're going to say, all right, X and X plus 4 are opposite, so those are going to get multiplied. And X plus 2 and X plus 1 are opposite, so they're going to get multiplied. Now, what you're going to do here is, remember that we just learned a second ago, either through FOIL or the rectangle method, how to multiply those two binomials. This left side is really easy. It's just going to be x squared plus 4x. That's the distributive property. Okay, so whichever method you can, use a FOIL or the rectangle, go ahead and do this part right now. So pause it while you do that, and then I'll go over how to do that in a second. All right, so I'm going to use the rectangle method because that's what I do in my class normally. Okay, so I'm going to put x plus 1 and x plus 2. I'm going to multiply each piece. Okay, when I get to this point, I have two pieces that can be combined, which is always here and here. So you can see I'm going to get x squared plus 3x total plus 2. And then, like I said, on the other side, you're going to end up with x squared plus 4x. Okay, so that's how I get to this point right here. Now, before you freak out and think, oh, I'm going to have to do factoring and stuff, notice that if I go ahead and take a second and subtract x squareds from both sides, those are going to cancel. Then I just really have a two-step equation. I'm going to subtract 3x from both sides, and I get x equals 2. It's really a one-step equation, I guess. So the only thing else that you could do from here is I could say, hey, so what are all the segments equal to? In which case you would take that 2 and you would plug it in and get 4, 2, 3, and 6. And you can check your answer that way too. Is 2 times 6 the same as 3 times 4? Yeah, it is. All right, so now what we're going to do, that's pretty much it for that theorem. The two things multiply opposite each other. So now what we're going to do is we're going to go ahead and look at things that cross outside the circle, which means it could be secant lines or it could be tangent lines. They're each going to have their own situation. However, unlike the other one, you would not have just two tangent lines because we've already had two tangent lines. Remember, if two tangent lines connect at a point outside the circle, they're equal. So we don't need to have that part of our theorem. We're either going to have two secant lines that cross 2 times, or one secant line and one tangent line. And we're going to look at those as separate pieces, even though the theorem's very, very similar. So first we're going to look at this piece right here, this piece of your notes, which is page 12. All right, so the theorem says for two secant segments that cross outside the circle, okay, so again, it's called a secant segment because it's not a line, it stops, like the picture right here, okay? So it's segments, they're not lines. They cross outside the circle, meaning they cross at this point right here, okay? They cross there. Each product of the outside of the secant with the whole segment secant is congruent. To me, that's always very confusing. So what it's saying is, it's saying if you take just the outside by itself, okay, so that this piece, I'll use a different color so we can see it a little bit easier. So if I take just the red piece, okay, and then I multiply it by the whole thing, meaning this whole piece right there, all the way across. Let's call that W or something, okay? So if I take the outside and multiply it by the whole thing, that is equal on both of them. So on this one, okay, if I multiply that whole thing, we'll call that D. So this time we have, again on the outside, E times the whole thing is equal to S times the whole thing. Now we don't have to make up a third letter because we already know what this is. If this outside is S and this is T, the whole thing is S plus T. If this outside is E and the whole thing is, or the inside is F, then the whole thing is E plus F. So if you look at the theorem, it says this. The outside, which is S, times the whole thing, which is S plus T, is equal to the outside, E, times the whole thing, E plus F. So it's kind of a hard one to remember because you're going to want to do E times F and S times T because that's the rule for the inside. It's not the same though. You have to take your time. You have to remember the rules are different. And you have to remember that we're looking at this whole entire segment this time. So let's do some with some practical applications so we can see it. All right, so here's the first example you have on your paper. The first thing we have to do is we have to identify what are our outside segments and what are our inside segments. Okay, we know that we're going to be setting up basically an equal piece here. So first thing I do is I look at my outside. I've got 6 on the outside, and on the other side, I've got 5 on the outside. Okay. So now all I have to do is figure out what's the whole segment. Well, for 6, the whole segment is 9 plus 6, which is 15. Okay, this whole thing is equal to 15. No, I know that. On the bottom, it's not equal to 5x. It's equal to 5 plus x. That's a very common mistake. So in here, I'm going to have 5 plus x. So that's what you're going to see on the screen here. As you can see, I've got 5 times 5 plus x and 6 times 6 plus 9. Simplifying, of course, I'm going to distribute on the left side. I'm going to get 5x plus 25. And on the right side, I just combine the 9 and the 6 as I did when I was doing the practice up above. Now, 6 times 15 may require a calculator. It turns out it's going to be 90 because 6 times 10 is 60 and 6 times 5 is 30. Okay? Then I'm going to subtract 25 and divide by 5. I get 13. Remember, it's very easy to check your answer. I'm going to take that 13 up here, and I'm going to say 9 times 6, as we know, 9 times 15 is 90. Check to make sure the other one works. We're going to do 5 times 5 plus 13 is 18. And that also works out to be 90, so we know we did it right. It's very important that when you have the opportunity, you check it. A lot of you guys make mistakes on angles where you have an angle of 150, but it's clearly a cute small angle. Not that the picture is guaranteed to be right, but usually the picture won't make any sense if it's not drawn pretty accurately, or at least pretty close to accurately.
Okay, so let's move on to the next problem. Okay, you may have to label a couple of these things in your notes. Alright, so again, we're going to go ahead and we're going to focus on looking at the outside times the whole thing. So here's my outside, done in yellow, and then the whole thing done in red. So in this case, we're looking at the outside being just 6, and we're going to multiply that by 6 plus the inside as well, which is 4. So altogether, we're looking at 6 times 6 plus 4. That will be equal to, okay, the outside of this one over here which is x plus 2. And we're going to multiply that by the whole thing, which is x plus 2 plus what's on the inside, which is 11. Okay, you can combine these two and make 13. So you pretty much end up with that stuff right there. So as you can see, this is what I have on my paper as well. So what I did here is I went ahead and combined 2 and 11 and made 13, and I also did the multiplication on the right side. Okay, from there, if I want to go ahead and multiply those two things, you could either use FOIL like we talked about earlier, or you could use the generic rectangle that I showed you guys. So to do that one more time, make a generic rectangle, x plus 2, x plus 13, and if you multiply each of the sides, okay, as you can see, you're going to end up with 15x between these two, and the rest of it's kind of self-explanatory. Subtracting 60 from both sides, we end up with negative 34. You could go ahead and look at that problem as a diamond, trying to find a diamond problem. And that's what we're going to do on this one. So now that we know that the problem is as you see on top, we're going to go ahead and put negative 34 on top, remembering those two go together. The 15 goes down on the bottom. And the two things that multiply to equal negative 34 and add up to equal positive 15 are 17 and negative 2. From there I put those inside the rectangle. The outside then is quite easy to fill in. As soon as I have the outside, I'm simply going to set each of them equal to 0. And I end up with 2 and negative 17. Going back to our problem, both of these answers don't make sense. Okay, a negative 17 doesn't make sense for a distance. So it doesn't make sense for this answer right here. So the answer must be x equals 2. Now we're going to move on to the next page of notes. Make sure you have that. Okay, what we're going to look at now is we're going to look at when we have one secant and one tangent. So instead of having two secants like we did in the last one, this is the same rule, it's just I actually think a little bit easier. So first, we have our outside. We have our outside. Okay. And then we also have our whole entire segment, which is G plus H, so it's made up of that and then including this as well for the whole thing. So we end up with is, you end up with G times G plus H, which I'll do in different colors so you can see it. Okay, and what we end up on the other one though is if we look at it as the outside is P, but the outside is also P, and the inside is P. So when we think about, there is no inside, but when we think about the whole thing is just what's outside. So that's why it ends up being P times P, because it's the outside times the whole thing, and they just happen to be the same. And that's equal to G times G plus H. Alright, so let's look at an example. You're going to have to fill in the 8, the x, and the 16, I believe, on your paper. Alright, so using the logic from before, we've got x on the outside and 8 on the inside, so it ends up being x times x plus 8. And then on the right side, because of the fact that 16 is a tangent, it's just 16 times 16. That gives us 256, and on the left side I went ahead and distributed this x. So I said, alright, x times x gives me x squared, and x times 8 gives me my 8x. Now I'm going to subtract the 256. This is not one that I can think of an easy way to factor it. Now, when you're doing this problem, you can try to think of other numbers that would work in there. The problem is 16 times 16 is such a large number. on previous problems, we might have been able to figure out the answer just simply using some problem solving skills. Alright, so now what we're going to do is, if we can't think of a way to factor it, which I can't, the only thing left to do is the quadratic formula. Remember, the quadratic formula is negative b, this is why it jumps to negative 8, because b is 8, plus or minus square root of 8, so it's b squared, minus 4a, which is 1, times c, which is negative 256. On the bottom we also have a. So remembering again that the number here would be a if there was one. This is always b. This is always c. Again, it's just so we can talk about these things. Then this would be a, which hence makes sense with the 1. Okay, this would be b and also b, which is again why you end up with 8 in both of those situations. And the final one would be c, which again came from manipulating the problem and moving things around. Okay, now you can see here I went ahead and I squared 8 squared, and I multiplied negative 4 times 1 times negative 256. What we end up here is we end up with two answers. As you can see, I got rid of the minus sign because if you're starting out with a negative and you're subtracting, it's just going to get more negative. So if you take just the positive answer, you end up with 12.49, or approximately so. Okay, so thank you for watching the third and final piece of our videos about circle theorems. Hopefully this has helped you. Make sure you're studying, asking lots of questions. This is a difficult concept, and we will be talking about it more in class soon. All right, thanks.